Hello and welcome to Unit 6. We are moving beyond differentiation now, although not leaving it behind, and we're starting to explore the ideas of integration. The two big ideas in calculus are the tangent line problem, which we've been talking about, and the area problem. In the tangent line problem, you saw how the limit process could be applied to find the slope of the tangent line, or the derivative, at any point on the curve. A second classic problem in calculus is in finding the area under a curve that's bounded by the graph, the x-axis, and any two x values. So what's the relationship between the graph of a rate of change function, a derivative, and the area of the region between that derivative graph and the x-axis? Well, imagine that a hurricane hits Colorado Springs, okay, and your house is flooding. To save your flooding home, you rent a pump that can remove water at a rate of 500 gallons per hour for the first 8 hours of pumping. But as the storm grows stronger, you get a second pump, and for the next 16 hours, you can remove 900 gallons per hour using the two pumps together. So we're going to illustrate this scenario on the graph here. On the x-axis, we'll have time in hours, and on the y-axis, we'll have gallons of stormwater. So for the first 8 hours, you can remove 500 gallons per hour. So we get an area in that rectangle of 4,000. Now we have to up our game because the storm is growing stronger. You get a second pump, and for the next 16 hours, we're doing 900 gallons per hour. So the area of that rectangle is 14,400. When we say area under a curve, this represents the area between the graph and the horizontal axis. So what's the area under the curve between 0 and 8 hours? And what does that represent? 4,000 is the area, and that represents 4,000 gallons of stormwater that was removed during the first 8 hours. What's the total area under the graph? The total area is 4,000 plus 14,400, which is 18,400, and that represents the total gallons of water removed in that 24-hour period. The problem is, not all graphs are rectangular. So how do you find the area under a curve? Like this curve, perhaps. Well, we know we can find the area of a rectangle, so I suppose we could just do our best with that. But you can see there's area on the top left here that's not filled in, and then over to the right a bit, there's area that is filled in that shouldn't be in the rectangle. I guess we could use some smaller rectangles. That helps a little bit. Maybe even smaller rectangles. Now I feel like we're getting somewhere. It's getting more and more accurate. How about a bazillion rectangles? We can find the area under a curve in the interval AB by approximating a collection of inscribed or circumscribed rectangles in such a way that the more rectangles we use, the better the approximation. And if the number of rectangles is increased without limit, then boom, we get the area. And this is known as integration. By using rectangles, we can see that there are 4 different ways of approximating the area, and this method is commonly known as Riemann sums. Consider a 30-gallon aquarium is being filled with water at a rate modeled by 6 sine pi over 8t, where t is time in minutes, and r of t is gallons per minute. Find the volume of water in the tank after 5 minutes by using 5 rectangles that are 1 minute wide and r of t tall. So we're going to use this table. First column is time in minutes. The second column is both the height of each rectangle and the area of each rectangle, because area is height times width, and the width of each of our rectangles is just 1. And on the far right here, we're going to keep a running total of our area. So the first rectangle has a height and area of about 2.3. So far that's our total. Second rectangle has a height and area of about 4.2. So we'll add that to the first rectangle, and now the tank has about 6.5 gallons in it. And then we'll continue on adding rectangles, adding it to the total area. So by the time we get to 5 rectangles, we have a nice estimation here of about 23.725 gallons. But that's the problem. It's an estimation. Now, if we could use an infinite number of rectangles, we'd arrive at the exact volume of water in the aquarium after 5 minutes. We can't actually use an infinite number of rectangles, but we can take the limit as the number approaches infinity, and this is called a definite integral, and it's represented by this notation here. And we'll talk about that a little bit more next class. There are 4 main types of Riemann sums. A left Riemann sum, because as you can see, the top left of the rectangle hits the function. Or we could have a right Riemann sum, where the top right of the rectangle hits the function. We could have a midpoint, where the midpoint of the rectangle of the top hits the function. Or we could have a trapezoidal sum, where each top of the trapezoid, it's not a rectangle anymore, hits the top of the function. So let's explore these. For the function shown at the right, we're going to draw some rectangles forming a left-hand sum in blue. All right, so we want delta x to be 2, which means the bottom of each rectangle has a width of 2. This is a left-hand sum, so that upper top left corner of the rectangle is what hits the function. So that has a height of 8. And then the next one has a height of 7. And the next one has a height of, 5? All right, so we have a width of 2 on each of them, and then various heights. So if we wanted to find the area of those, we have a width of 2, and then we can add the heights together. And so we have an area of 40. Now let's try this again with a right-hand sum. Same graph, but this time my rectangles are going to hit at the top right. So that one has a height of 7, then a height of 5, oh, and then that little guy, he has a height of 1. So the area of those rectangles is 2, that's the width of each of them, times the heights added together, which is 26. Well, one of them overestimates, one of them underestimates. The left-hand sum, as you can see, overestimates, and the right-hand sum underestimates. Let's try a different curve. Same process though. This time our delta x, or the width of each of our rectangles, is a half. So the first one, that's a little guy, height of 1, then a height of 4, then a height of 6. So we find the area of that, 0.5 is the width of each rectangle, and then the heights added together gives us 5.5. Now we'll try a right-hand sum. top right corner hits the function. So we have a 4, a 6, and a 7. 0.5 is the width times each of the heights, and we have an area of 8.5. Well, this time, the left-hand sum underestimates and the right-hand sum overestimates. So actually, based on a function's behavior, we can know, given a Riemann sum, which one is going to over or estimate the area under a curve. If you have an increasing function, the left-hand sum will underestimate it and the right-hand sum will overestimate it. If you have a decreasing function, the left-hand sum is an overestimation and the right-hand sum is an underestimation. In addition to left and right-hand sums, we can also use midpoint and trapezoidal sums to estimate the area under a curve. So this time, it says using geometry, because geometry, we know the area of a lot of different shapes. So the area under this graph is a trapezoid. So we have the function 1/2 x plus 1 on the interval from 0 to 5. And the area of a trapezoid is 1/2 times the height times the bases added together. So the height of this trapezoid is actually kind of what it's lying on. It's on the x-axis. The height is 5, and then the bases are the two parallel sides. So we have the left base is 1, and the right base is 7/2. So we can just find the area of this trapezoid. 1/2 times the height, the bases added together, gives us 45/4 units squared. So for exercise 7, we're kind of going to pull all of this together. The table below represents the velocity in feet per second of a car traveling on a straight road over a 50-second time interval. So each of these dots here is represented by one of the heights on the table. We're going to start by estimating the total distance the car traveled using a left-hand sum with 5 subintervals. Now for a left-hand sum, the top left hits the function. So this first rectangle has a height of nothing. Then we have another rectangle that hits at 20. And then there's another one that hits at, what is that, like 52. And then another one that hits at 80. And then the last one, let's see, what is that, 40, that hits at 77. So if we want to find the area, the base for each rectangle is 10. And then we just add each of the heights together. So 2,290 feet. That's how far the car went. Same process, but now let's try a right-hand sum. So the first rectangle hits 20. Then the second rectangle hits 52. And then 80. And then 77. And 74. Again, the base for all of them is 10. And then we add all those heights together, multiply it times the base, and the right-hand sum gave us an area of 3,030 feet. Now we'll do a midpoint sum, which we haven't seen yet, but it's the same process. It's just that the rectangle hits smack in the middle of the top. So we've got the first one hits at, what is that, like 14, and then 28. There we go. There's our midpoint rectangles. The base of each of the rectangles is still 10. The heights are just in the middle, and we can see what the heights are from the table up here. So 14, and then 28, 70, 86, and then 70 again. Right, so the area of that one, the midpoint, if we figure that out, is 2,680. Unsurprisingly, That's between the left-hand sum and the right-hand sum. Now the trapezoidal sum is a bit different. Let's just draw in our trapezoids first, and then we'll figure out how to find the areas. So the first trapezoid in the first section is actually, well, it's kind of a triangle. And then the second trapezoid goes here, here. Okay, so those hit the function, and then the rest of it, there you can see the trapezoid. And then the next one, next one, next one. The area of the trapezoid, 1/2 times the height times the bases added together. So we always start with 1/2, and then the height of each trapezoid is 10. That's what's on the x-axis, so we can put a 10 there. Now we have to add all of the bases. So watch carefully. For the first trapezoid, the first base, which is actually like what's going on the y-axis, is 0. And the second base is 20. But that 20 is used both for the first trapezoid and the second trapezoid. So let's write that down. We've used 20 twice. And then for the second trapezoid, okay, we've already have our 20, and then the next one is, what is that? 20 goes to 52. But that 52 is used on the second trapezoid and the third trapezoid. So we use 52 twice as well. And then at 30, we use that one twice at 80. And then we use 77 twice. And then this last guy only works for the fifth trapezoid. We only use him once. And then putting all that together, we get a trapezoidal sum of 2,660 feet. Now, just for fun, let's find the average of the left and right hand sums. And how does this compare to the trapezoidal sum? Well, the average of the left and right is 2290 plus 3030 divided by 2, which is 2660. Look at that. All of this is going to be the basis for some really cool stuff we're going to be doing throughout Unit 6. As always, I'm glad you've joined me. Thanks for being here.